So I will start with addressing the questions of how biogeochemical model deals with nutrient retentions, then try to introduce the applications of a process-based biogeochemical model, the RiverStrahler model, at a large scale, and finally raise the questions of are biogeochemical model useful when designing policy option for the future. So for this first part, how biogeochemical model address nutrient retentions, I will try to use my own experience of nutrient model, so it won't be an exhaustive review of all existing biogeochemical models. I will just try to point out the merits and the limits of each approach, and finally introduce the model I'm currently working on, the RiverStrahler model. So, starting with the most empirical approach, the simple input-output regressions, where the retention within the watershed is calculated as the fractions of the net input that is not exported at the outlet of the river basins. We have the NANI model example, which assume that the net sum of anthropogenic nitrogen input is actually an excellent predictor of nitrogen delivery at the outlets. In this model, the independent term here represents a kind of nitrogen background, while the regression factor here, 0.226, implies that as a mean, 74% of nitrogen is retained within the watersheds. They have also proposed to correlate this retention factor according to simple climatic variables, and by doing so, enabling the implementation of the NANI model across the world and under different climatic conditions. Nevertheless, such input-output regressions have only a poor capacity to explain the retention processes. So if you want to do a bit better, you can use a partitioned retention model that add a further distinction between what is retained within the landscape and what is retained in streams. In this approach, diffuse sources are submit to landscape retentions as a functions of hydrological properties and also the fractions of forest and wetland if riparian retention is taken into account. While on the other hand, aquatic retentions could be calculated as a functions of either the river length, the drainage density, or sometimes the residence times. I have used for a couple of times the green model that is actually a nice example of spatially explicit partitioned retention model calibrated for the whole Europe for calculated total nitrogen and total phosphorus exports on an annual basis. And actually, these time resolutions prevent this kind of partition, most of the partitioned retention model, to reveal the variability of the hydrology in the retention process. And they also leave some unanswered questions about the exact nature of the retention and where does it happen in the watershed or in the in-stream parts. So finally, only process-based model can address this issue if they are implemented at a thinner time resolution. And I think Don has already introduced the SWAT model, so I won't do all these presentations, but SWAT is a semi-distributed, physically based model representing the interactions between soil, vegetations, and water. It makes the distinction between what's happened in the land phase using the HRU concept and what happened within the river streams using the Qual2E model. Another process-based model is the RiverStrahler model, which I am currently involved in the development. It explicitly calculates the retention and the cycling of different nutrients in different forms of carbon, nitrogen, phosphorus, and silica in the river. It is one of the few semi-distributed model applied at seasonal time resolutions and adapt for small and large regional watersheds. So strictly speaking, the RiverStrahler model is a drainage network models representing the kinetics of processes in the river, but not the processing occurring in watershed soils. The genericity of the RiverStrahler model lie in the assumption that the singular functioning of an aquatic systems lie in the variety of constraints that are applied to these hydrosystems, so mainly hydrological constraints, climatic constraints, water fluxes, point sources, and diffuse sources, and therefore an accurate description of all these constraints is the key to understand the functioning of any hydrosystems. So there were a couple of papers comparing these different approach, and they state that the retention is rather coherent, whatever the model that is used, but they also state that all these models have been built with different level of complexity for specific purpose. For example, linking anthropogenic pressure with nutrient riverine exports is the aim of the NANI model, while performing a source apportionment of nutrients is what green can do. And if you want to quantify the role of the different processes and pathway, you have to go for a process-based approach. And I will now focus exclusively on this model, the RiverStrahler model. So this is the second part of my presentations. And I will introduce the work we have done to propose a continental application of this model describing all microscopic process within the water column. So, considering the number of state variable simulated by the RiverStrahler model and the time resolution, that is 10 days, one of the main concerns was to define scalable simulation units to save calculation time and to be consistent with a large-scale application. So we have defined three types of objects that are simulated. The first type of object are the upstream part of the drainage network, where the network could be simplified as a suite of hierarchical stream order according to the Strahler ordination. And we are averaging characteristic for each Strahler order. We can also describe main branches with a kilometric resolutions, and we connect the different upstream part to the main branch, or either one branch to another branch. The third type of objects are reservoirs that are here considered as perfectly mixed reactors that are connected to the main branch. So we try to analyze this Northeast Atlantic continental domain that is more than 1 million square kilometers and almost 400,000 kilometers of cumulated river. And we have applied these modeling units with a selection of all river basins greater than 300 square kilometers. So we end with 17 main river basins from the Rhine, the Seine River, the Loire, etc., until the Guadalquivir, and a lot of smaller basins. So the biggest river basin are subdivided into smaller objects, smaller modeling units. So the challenge now is to provide input information for the RiverStrahler model scale for these modeling units. So I will review the different type of inputs, starting with the morphological information. So we have used this CCM catchment characterization and modeling database available for the whole Europe and providing relevant information regarding the morphology. For light and temperature, we have used empirical relationship to cover the gradient of latitude from the Rhine to the Guadalquivir. Water fluxes were not modeled. We have used long chronicles of observed discharge, and we have then calculated base flow index and use hydrological filter to separate the surface fraction of the discharge and the base flow. Point sources were derived from this EEA waterbase, European Environmental Agency database. And it was actually a nice database providing a spatially explicit census of all wastewater collection, their connection to sewer and the wastewater treatment plant, plus the exact locations of their point of discharge to the hydro systems. So you can use these informations as a direct input to the network. For diffuse sources, as I say, RiverStrahler is strictly speaking a drainage network model. It means that it does not represent process occurring in watershed soil. So we have to define method to estimate diffuse sources. And in the case of nitrogen, we have used the work of La Saleta, who developed these generic representations of agro-food systems, the graphs approach, using statistics from Eurostat and using nitrogen as a tracer of nutrient cycling in the agro-food systems. And actually, it just used this Eurostat to and downscale this information according to land use informations to get a specialized nitrogen budget at a higher resolution. For other nutrient sources, we have combined and downscale different European data sets to estimate nutrient-leaching concentrations. So we have used, for example, this Luca measurement available for the whole Europe and giving soil content for organic carbon, phosphorus, and also silica, I think. We have used some model output for erosion. And finally, using all this inventory of European and country-specific data sets, we managed to get a set of continental map of land-based nutrient emission to the river. One last thing that we had to do when trying to apply the RiverStrahler model at a large scale is also to develop a database to gather all the information available about nutrient measurements in river. So we developed this donuts database for database of observed nutrients in rivers with the idea of providing a standardized access to these informations. So it actually merged 30 data producers across 10 countries with a lot of variable entries, several 10,000 of monitoring stations, and more than 50 million of records for both water quality and water quantity. So just to show you the spatial distributions of this monitoring station, I just add two maps that there is no point to analyze this map. There is just something to show you the spatial distributions of here discharge data for the period 2000-2010. And the same for water quality, and I just pick up nitrate concentration. So all this pre-processing of data and database building has been introduced in a modeling platform called PyNuts, nuts for nutrients, and Py because it's written in Python. That actually allow you to derive from a set of pre-selected databases all the information required by the river model as input and pre-calculated at the scale of our modeling unit. It also includes the estimations of diffuse sources using the graph approach, and also the retrieve of observation, especially for water fluxes, because as I say, we didn't model water fluxes, we have used observe discharge. This PyNuts modeling platform also aims at piloting the RiverStrahler simulations and compare the simulation to the observations. So the validation time frame in this exercise is somewhere between 2007 and 2010, as it corresponds to the period where most of the input data are overlapping. And I will just show you some validation example at the outlet of the main river. So here are some concentration for nitrate at the outlet of the Rhine River and the Dordogne, ammonia concentration for the Seine, dissolved silica for the Meuse, phosphate for the Seine, total phosphorus for the Tage River. I will not go through the whole list of all outlets and all variables simulated by the RiverStrahler model. If you want to see more validation, you can access the EMOSEM report. I will give you the link at the end of the presentations. And you will also find in this report the work we have done on simulating scenario, prospective scenario, with scenarios strictly based on regulations and some other scenario more, I would say, alternative or assuming a more radical change in practices. And this is actually the aim of the last part of my presentations. Can biogeochemical model guide socio-ecologically relevant policy options? So the development of the Peanuts modeling platform was done within the time frame of the EMOSEM project, with the idea of coupling these river simulations with three different marine models. The Miro & Co model for the Belgian part here, the EcoMars 3D model for the French marine area, and the MOID Life model for the Spain and Portuguese marine area. The aims of the EMOSEM project was to assess the impact of mitigation measure to reduce nutrient fluxes export to the Northeast Atlantic domain and their capacity to limit associated eutrophication problem. So the idea was to use this Peanuts modeling platform that actually provide an operational tool to assess the impact of the agro-food system on the hydro systems. And so in agro-food system, I include both the agronomic part and also the human release by wastewater treatment plants. And the idea was to assess three different scenarios. The first one was mimicking the compliance with the European Urban Wastewater Directive. The second one assuming good agricultural practices, and a third one that imply a more in-depth reshaping of the whole agro-food system with relocalizations of agricultural productions, a change in agricultural practices, and also a change in human diets. So I will introduce in terms the storyline of each of these scenarios and how we have built the input data, and then provide the environmental assessments for each of these three scenarios. So for the first one, we have used this EEA water-based with this spatially explicit census of all wastewater treatment plants and the exact places where they release their wastewater. And we have applied the recommendations of the directive. So we have upgraded the treatment in wastewater treatment plants according to the size of the agglomerations and also the sensitivity of the receiving area that are here in color. So the dots that you see here in color are wastewater treatment plant that has been improved under this scenario. So T1, T2, and T3 stand for primary, secondary, and tertiary treatment with possibly additional treatment for nitrogen and phosphorus. And it's striking that there is only very few wastewater treatment plants mapped here because in this Western European country, most of the wastewater treatment plants actually comply with this European directive. Introducing now the GAP scenario, so GAP for a scenario that follows the good agricultural practices. As I say, we don't have an agronomical model that represents the process within soil watershed, so we have to find a way to link a change in agricultural practices and a change in lixiviation to the agrosystems. And to do so, we have built two conceptual relationships. The first one allows us to link the total amount of nitrogen applied to agricultural yield, and actually the difference between the one-to-one line and this dot is actually the agricultural surplus. So by using this relationship, we can estimate agricultural surplus, and then we have to build another relationship to link surplus with lixiviation to the agrosystem. And we have here used the work of one of our former PhD that have worked specifically on this subject. What is surprising is that if you look at this trend that is starting in 1961 to 2009 for France, you see that actually the agriculture practices have improved a lot, and there is a continuous increase of agricultural yield, first with an increase of nitrogen input here, but then input start to stabilize and even decrease, but agricultural yield continue to increase. So it means that we have already considerably reduced nitrogen surplus in France. So we are not, we didn't reach an equilibrated fertilization, but we have considerably reduced nitrogen surplus. And the only or the main remaining lever is actually the introductions of catch crop before spring crop to follow the recommendations of good agricultural practices. So to introduce this last scenario, which is a local, organic, and demi-terrien scenario, it assumes that the extreme specializations of agriculture is the main cause of nitrogen losses. And only an in-depth reshaping of the whole agro-food system could be efficient to reduce these losses to the environment. So the first assumption of this scenario is that we change human diet by halving the consumptions of animal protein. By doing so, we can then adjust livestock size to the requirement of the local population. And that was the result for France. So you have here the commercial fluxes of meat and milk, and you have here density of livestock expressed as livestock unit per hectare of agricultural land. The third assumption is that as a complement of animal manure, we introduce legume in long and diversified crop rotations with no add of synthetic fertilizer following the requirements of organic farming. And we add also a PhD student that has defended very recently, and she was analyzing the performance of both conventional and organic agricultural practices. And you can see here that for the same amount of fertilizations, the yield are quite comparable. So I will now jump to the environmental assessment of this scenario using the peanuts modeling platform. And I will mostly focus on nitrates, essentially because this is the main issue in this area. So here is the map for the reference situation, so nothing new. I mean, very poor quality in northern part of France and Belgium. If we implement the first urban wastewater treatment scenario, if we go back and forth, we see a slight improvement downstream the Paris conurbation here, also in the Tage River and I think in the Thames. But as I say, most of these countries already comply with this directive, so there is no much expectation. The improvement is much more visible when implementing the gap scenario, especially for Spanish and Portuguese part, and also the upstream part of the Rhine River that managed to recover good standard quality. And the more efficient scenario is actually the more radical one, which mimic a more local, organic, and Demeterian regime. And it is more striking if you just passed from this log ORGDEM scenario and the reference situations. So I will now continue with a zoom on this specific area to show you more results. And here are nitrogen fluxes exported at the outlet of the Seine River. So you have here the reference situations with the seasonal variability and also the variability of the hydrology, because we have tested 10 years of hydrology for each scenario. You get also, again, this red reference here, and you can see the change in nitrogen export fluxes under the free scenario. So at the mean, as a mean, we reach 6% of decrease under this wastewater treatment directive scenario, 30% of decrease in nitrogen fluxes applying good agricultural practices, and 55% with this local organic farming and Demeterian scenario. The idea was then to feed marine model with these nutrient fluxes, not only nitrogen, but also phosphorus, silica, etc. And here is the simulation provided by the EcoMars 3D model, so developed at the IFREMER in France. And one nice result is to see, so you have here diatom biomass and here dinoflagellate biomass. And we demonstrate here that you can limit, I would say, completely erase the issue of dinoflagellate here in the Bay of Seine without altering the productions of diatoms. So, to summarize, we have demonstrated limited impacts of scenario based on the current regulation options, mostly because Western European countries almost fulfill this, the requirement of these two scenarios. We also demonstrate that exploring more radical options like local, organic, and Demeterian scenario show that there is room left to reconcile agriculture and water resource protection. And in our opinion, it should be the duty of River Basin Model to help in the biogeochemical accounting of this alternative storyline, then perform the environmental assessments, and finally produce targeted recommendations for nutrient management on Watershed. So as a conclusion, I would say that the development of this Peanuts platform has led us to a paradoxical but fruitful complementarity between, on the one hand, the RiverStrahler model, so mechanistic models providing a detailed descriptions of microscopic processes occurring in the aquatic system, and on the other part, a more conceptual representations of the agro-food system, which has the merit to enable the assessment of a territorial recognition far beyond the topographic limits of Watershed. So, if I have to put something into perspective, I will just use this simply scheme that represents the link between the scenario definitions, the preparation, the building of model input, the use of biogeochemical model to perform environmental assessments, and add that each biogeochemical model has its own data requirements. And the more complex biogeochemical model you have, the more complex input data you need to provide. And it might be possible that the complexity of these inputs prevents us to, I would say, define ambitious or radical scenario to put in into perspective. That's it. Thank you. Yeah.
Oh, sorry. Okay.
Yeah.
When you were doing the reduction in animal proteins, how did you just take all animal types and have all of them, or did you do a transition away from cattle completely and then down to just chickens? Like, how was that reduction done?
Actually, I didn't do this part of the work. It was the work of La Saleta, and I think, I'm not no. Okay, I thought I put an extra slide for this. But I think we just reduce the amount of animal protein to 35% in the human diet. And I think we keep the ratio between pork, chicken, beef, and maybe after you add something if you... yeah, I should have added this extra slide because it was informative, but yeah. Philippe or John?
Just putting the first part of your talk about where retention occurs in the landscape versus in rivers together with the scenarios part, how much retention in that region happens on land versus in rivers in your modeling exercise, and how does that change as a function?
Across the scenario?
Yeah.
Yeah, that's a difficult question. No, I wouldn't give you a number because I'm not so sure.
But is it mostly on land or mostly?
I mean, the retention within the river is not changing a lot across the scenario. I mean, it's not linear, otherwise it's not worth to do model, but it's not changing a lot.
My question is also how important are in-stream processes compared to, of course, the loading on the land?
Yeah.
So maybe it's once you start having reservoirs and dams and things like that.
Yeah, yeah, but yeah.
But I had a technical question. Your scenario implementation, how do you implement your scenarios? Is it instantaneous change or is it?
Yep. Yeah.
Because that's probably also.
Yeah. Also because we are not assuming that we are going to move slowly to this kind of radical scenario. We just I think it's worth to have such extreme scenario to put on as a picture for the future and just have time to see if we are going this way or the other way around. So that's a bit this figure. So this is what we are doing. So we put 2000, but yeah.
I'm not very familiar with the model, the RiverStrahler model. So I'm just wondering, how much detail can you go into about agricultural practices? So like, so in the organic climate, are you actually changing anything beyond just application rate and crop grown?
Okay, so this is not part of the RiverStrahler model. As I said, the RiverStrahler model is only for the drainage network. And so the idea was to couple another approach that is basically the graph approach developed by La Saleta to represent the cycling of nitrogen essentially, but now we're also doing it for phosphorus and carbon within the agro-food systems. So maybe this can help you when we have construct this local organic and Demeterian scenario. We have used these agro-food system representations. And then, so this is, just look at the upper part of the figure. This is we are performing the analysis by region, so not within the watershed. We are using numbers that are provided at the regional scale. So these are two regions in France, Picardy and Brittany. Picardy is oriented toward intensive cereal productions, exporting a lot of its production outside of the regions, while Brittany is more oriented toward intensive meat productions. So this is two different systems, two different agro-food systems where nitrogen is circulating as in a different way in these two systems. And when we developed this local organic and demi-terrien scenario, we consider that we will halve our consumption of meat. We decrease livestock density in the area, and we just try to have all the number that fits all together. And for one of the most difficult parts was to assume, or to not assume, to determine the crop yield under changing agricultural practices. So if you move from conventional practices where you put fertilizer on to something more organic, then we have to figure out how our agricultural yield changing. And that was the work of the PhD here.
I thought this was really interesting work. I had a question about your scenarios. And usually when I think of agricultural scenarios, I think of things like cover crops and tillage and things about the agricultural practice. And your scenario had major changes to people's diets. I was just wondering, when you present these results, what kind of feedback you get about changing people's diets, and whether that's feasible or how that could happen?
Actually, looking at this idea of changing diet associated with organic farming practices, it started with a paper in 2009, and we did something not so, using empirical data and not so elaborated. And many people say, no, it's not realistic. You cannot convert everything to organic farming and change people's diets. And then we launched two PhD on the subject. One was looking at the performance of organic farming, and the other one was measuring lixiviation under organic farming, lixiviation of nitrates. So, and it helps a lot to convince people that organic farming could have good performance. And then we have to explain people that we cannot just only say, okay, just move from conventional to organic farming, because if we want to have a balanced nitrogen budget at the scale of the water food system, we also have to decrease and especially relocate meat production in France. And I think people start, at least in France, to be more receptive to this kind of informations. And we actually are implied in a lot of projects where called participative science, where agriculture are involved, water authority are involved, and they play the game, I would say. And especially we are actually starting a new project, and they will test, for real, the scenario that we proposed. So I think they are quite open to at least see what will be the potentiality of such radical change.